Let's get started because I have a lot to say. Now, today in this project, we go back to a very well-known result of Muhly and Solel. They prove that right here, they prove that two injective C-star correspondences are Morita equivalent. If that's true, then the corresponding Cuntz-Pimsner algebras are, I should say, strongly Morita equivalent in the sense of Rieffel. I mean, the Cuntz-Pimsner algebras, there is an impermittivity bimodule between the Cuntz-Pimsner algebras. Now, again, what does it mean to have these two C-star correspondences to be Morita equivalent? It means that we have an impermittivity bimodule giving us this isomorphism. Now, our motivation initially was to prove a more generalized version of Muhly-Solel result. We are not assuming our C-star correspondences to be injective. However, our technique is different. Instead of proving this result directly, we are defining two categories and we are building a functor between them so that the functoriality is going to imply, it's going to give us the generalized version of the Muhly-Solel result. You'll see how we are going to come back to this, but first let me introduce you our categories. First, Enchilada category of C-star algebras. Our objects are C-star algebras, and a morphism from A to B is an isomorphism class of AB correspondences. Now, when we say an AB correspondence X, we mean a right-Hilbert's B module, and the left action is defined by this non-degenerate homomorphism. Composition is the isomorphism class of balanced tensor product. Identity morphism on A is this guy as expected. And we have the zero morphism. For convenience, we drop the brackets, but whenever I say morphism, I do mean isomorphism classes. I want to take your attention to the fact that we cannot just get an AB correspondence X as a morphism. In order to make this a category, we actually do need to work with the isomorphism classes. Now here is our favorite ideal. For any given X, we are going to denote it by Bx. It's just a closed linear span of these guys. We will be using this ideal quite frequently. Now, here the difficulty in our category is that as our morphisms are not any kind of mappings, right? So just because we can go from A to B doesn't mean we can go from B to A, which makes calculations really difficult in the Enchilada category. So at the first place, what we want to do is for a given correspondence, for a given morphism here, X, we want to see what modifications can we do on this guy. For instance, this first lemma tells us what can we replace B by, or can we factor this? Now, here turns out we can, here instead of B, we can use any C-star subalgebra of B containing Bx, right? We want to Hilbert's module, right-Hilbert's module structure, so that's why we want it to contain Bx. And then once we do that, we get this very nice factorization that, again, we'll be using a lot. Now, of course, there are many properties that we needed to investigate in Enchilada category in order to work with this category. But because of time, of course, I cannot go through all of it. I just picked a couple of them that we are using the most. And the first one tells us what does it mean in Enchilada category to have two morphisms composition 0. Now that happens if and only if Bx is contained in kernel phi y. Here phi y is, remember, it's the associated non-degenerate homomorphism with this guy. Now, as you can imagine, a morphism being invertible, having right or left inverse is a very special case for us, and it's very useful. So we do want to give a nice characterization for those morphisms. The first one tells us a morphism in Enchilada category is right invertible. It has a right inverse if and only if it is a left full Hilbert bimodule. So here, when I say Hilbert bimodule, I mean it has a valued inner product satisfying certain property. And this statement has a dual. It has a right inverse if and only if, it has a left inverse if and only if it's a right full Hilbert bimodule. Well, let's combine these two. Of course, a morphism being invertible morphism are favorites, obviously, in Enchilada category. And those are imprimitivity bimodules. X is an imprimitivity bimodule if and only if it's either split monomorphism and right full or split epimorphism and left full. Now, the second category. This time, our objects are non-degenerate C-star correspondences. And morphisms from one correspondence to another is isomorphism class of AB correspondences, giving us this isomorphism. So each time we'll have this commutative diagram. Now, notice that, now what does it mean, X and Y being isomorphic in this category? We can see that isomorphism here in this category means just like these two objects are Morita equivalent as C-star correspondences, and that's what exactly we want. That's why we define morphisms in this category in this way, and you will see the use of it later on. Composition is exactly the same as in the Enchilada category. Identity morphism on X is just this guy. Now, given a C-star correspondence X, what is the Cuntz-Pimsner algebra of a C-star correspondence X? It is the C-star algebra generated by the universal covariant representation of the C-star correspondence. However, our functor, now we're going to, as I said, we're going to define a functor between these two categories that I was just talking about. Our functor contains Fock spaces. Therefore, given a C-star correspondence for the Cuntz-Pimsner algebra and the Toplitz algebra, we are going to use the characterization that Katsura introduced by using Fock spaces, Fock representations. That's a little, I'll talk a little bit about that right now. But first, here is how we are denoting the C-star algebra generated by a representation. When we say representation, we have a star homomorphism here, right? And we have a linear map. And for each representation, we have the star homomorphism from compact operators to be. And yeah, when pi is injective, this guy right here is injective and T is isometric. Here, using all of these. Now, but how does what do the elements of the C-star algebra generated by a representation looks like? The elements of this guy is just like a linear span of these elements. But now let's go back and look, what does x to the n mean and t to the n mean? For a given x, again, we start with a representation, right? We're gonna denote x to the 0 a, x to the 1 x, x to the a, x to the 2 is x tensor x, and x to the n is just this. Each of these x to the n's, they're all AA. They can be both, if I can just speak, they can all be viewed as a C-star correspondence over A. And now, again, by using this linear map, we are defining this t to the n here, this linear map with this. Now, let's come to the Fock space. Fock space is just a direct sum of all these x to the n's. Now, what Katsura does is he is defining a representation for this C star correspondence x. Now, we need a linear map, right? And we need a star homomorphism. And here is our linear map, how it's defined. All the elements of Fock spaces are going to look like that. See, really, all what we are doing here is we are taking this guy and tensoring with each summand. This should be y. There's a typo here. And here is how the star homomorphism is defined. Well, I just said this is an adjointable operator, so I should give the adjoint as well. And here's the adjoint. It's not as messy as it looks. Now I'm lying, it is. Anyhow, this representation is important for us because, so this is called the Fock representation. And Katsura proves that the C-star algebra generated by this representation is actually isomorphic to the Toplitz algebra. And it has such a pretty proof. So from now on, for the entire project, whenever we are taking an element from a Toplitz algebra, we're just, this is how the elements look like, or the linear span of these kind of looking elements. Now, notice that here Fock space is rightful Hilbert's A module. And also by using this injective non-degenerate homomorphism, we can view Fock space as an AA correspondence. And I'll just hold on a second here. I should mention this, that because we are using, when we are building our functor, we first needed to show that Fock space can be viewed as a TXA correspondence as well. And the Toplitz algebra TX can be viewed as an ATX correspondence. Now it's Cuntz-Pimsner algebra's turn. Katsura comes up with this famous ideal. We are going to call it Katsura ideal, and it's denoted by Jx. Extreme cases are possible, so Jx can be 0. In that case, the Toplitz algebra and the Cuntz-Pimsner algebra is the same. Jx could be A, just the entire A. And an example for that situation is when X is an impermittivity bimodule. And now this here, compact operators on this Hilbert module, this is a very important one for us. It's not easy to see at all, but this guy is actually an ideal of the Toplitz algebra. Now remember our Fock representation, when we compose it by this quotient map, turns out we are getting a covariant representation of X, an injective covariant representation. And again, Katsura proves that C-star algebra generated by this covariant representation is isomorphic to the Cuntz-Pimsner algebra. Now, from now on, whenever I talk about the Cuntz-Pimsner algebra, you can always think this quotient C-star algebra right here. Now we are ready for our functor. We are starting with two objects from the Enchilada category of C-star correspondences, and we take a morphism. Remember, when we take a morphism M, this is the relation that we have. First, we prove that this guy right here is an OX-OY correspondence. Now, the problem usually here when we are working on this project is that Fock space, Cuntz-Pimsner algebra does not act non-degenerately from left on the Fock space. So Fx is not OXA correspondence. That is causing a lot of problems usually, but turns out we can make it work. Now, this is not an easy correspondence to make calculations with, right? So we want something much nicer, a correspondence which will be much nicer and easier to work with. But in order to do that, I should show a couple of lemmas here. First of all, remember Fock space is an AA correspondence, and when you tensor it by itself, you get again Fock space. They're isomorphic as AA correspondences. And starting with an AB correspondence X, I be a closed ideal of B. This is the isomorphism that we get. Now, using the surjective homomorphism from the Topless algebra to the Cuntz-Pimsner algebra, we may view the Cuntz-Pimsner algebra as a TX-OX correspondence, and we can get this very useful factorization. Now, I'm going to skip this because I don't think I'll have time. Now, turns out this was the most surprising part for us, because this OX-OY correspondence turned out to be isomorphic to this much simpler correspondence. Even though fx is not OXA correspondence, these two guys are isomorphic as OX-OY correspondences. Now, I want to take a second to mention something. I have been GCM using JY here, but I said at the beginning, JY might be 0, right? There's such a case as well. So when we are doing these proofs, we needed to consider 3 cases when JY is 0, when JY is 0 and JX is A at the same time. Like they have, we need to like break it into cases and prove it that way. But regardless, in all cases, we prove that this is an OX-OY correspondence, and that will be our functor. Now, I'm going to come back to this. Let me first tell you what we are doing again. Let's remember what we are doing is, here is, think that this is the category of C-star, Enchilada category of C-star correspondences, and we are passing to Enchilada category of C-star algebras. Our objects are C-star correspondences. We are mapping them to their Cuntz-Pimsner algebras. And here, these morphisms, we are mapping them to this OX-OY correspondence. Now, in order to see this is a functor, what do we need? We need our map to preserve the composition and preserve the identities, right? And this, we have a theorem for that. It does preserve the compositions. I'm not going to get into details because of the time. And the preserving the identity part was pretty interesting. Let me first show here, you will see. Let's take the identity morphism here. So think like we are taking it here, you have an x2. So x to x, we should have an AA correspondence, A here, right? That's the identity morphism. Now, according to our map, this AA correspondence A, this should be mapped to this guy, right? But what is an identity morphism in the Enchilada category on OX? This, it's the OX-OX correspondence OX, right? So this has to be isomorphic to this, which was the most interesting part to prove, actually. It turns out it really is true. And of course, we do need a bunch of properties for that. But even though, again, fx is not an OXA correspondence, these two guys are isomorphic, turns out. So since they're isomorphic, their isomorphism classes are equal. So we are done. We do have a functor. Now, how did this gives us the generalized version of the Muhly-Solel result? Well, a functor has to preserve, it has to take isomorphisms from a category to the isomorphism in another category, right? And in our first category, isomorphisms are just isomorphism is just a Morita equivalence. And here in Enchilada category of C-star algebras, isomorphism is just isomorphism class of imprimitivity bimodules. Therefore, it gives us the result that we want automatically. And I think I am out of time, so thank you.